This is the fourth and final companion video from DeepSpace Storage for our quick start guide for Ceph environments. In this brief presentation, I'm going to talk about a little bit about the history of our catalog data service and systems managed storage. And then I will be moving on to a short discussion of our system architecture. So OpenSMS began in the 1990s at a period of time when the IT industry was migrating enterprise applications out of the mainframe environment and into the distributed client-server Unix operating environment. At that time, there was situational awareness that the Unix environment did not have the processes for data protection or data management that the mainframes had, and that this was going to ultimately lead to problems. And those problems had to do with catastrophic data loss occurring quite regularly due to usually operator error, as well as an inability to scale enterprise storage without any system-wide processes for managing, and the fact that we were trying to scale a storage platform that maintained the interactive user semantics of a file system, which was just at odds with the idea of creating a scalable platform that could be thoroughly regression tested. So although everyone seemed to understand that problem, the solutions were not forthcoming, probably in most part because it was a technically very complex problem to solve that required deep, close integration of a storage management solution into an operating system kernel. And at that time, the Unix market space was divided between perhaps 24 different proprietary Unix implementations. So from a system programmer perspective, the only way to have solved the problem would be to pick which one of those operating environments you wanted to try and solve the storage problem for, and then find the financial resources to license operating system source code. In 1995, a consortium of IT companies that were in the storage space tried to resolve some of these issues by creating something called the Data Management API, or DMAPI as we refer to it. The idea of DMAPI was to create an API that would be included in all or at least most file systems that would allow user-level processes to get file system events and do data management things without having to be closely coupled with the kernel. Unfortunately, the API was poorly implemented and embraced by almost no one. I happened to be in the audience of the IEEE Mass Storage Conference when that was announced, and saw an opportunity to at least get started developing a solution using DMAPI. So I followed it for a few years, and in roughly the 2000 or so timeframe, Silicon Graphics released their XFS file system into the open source community on their FOSS site, free and open source software. And that included all the software that I needed to build a Linux kernel that had DMAPI, so I was off to the races. Then in 2005, I had first prototype operable and published a paper at the IEEE Mass Storage Conference, again in Monterey, California, and introduced my architecture. Unfortunately, some merger and acquisition activity a few years later brought my project to an end after Sun Microsystems bought the company I was working with, Storage Tech. And it would be a few years after that, in 2016, that some colleagues of mine and I would form DeepSpace and start work on the project again. So that's a little bit about the history. It's been in the works for over 25 years now. So we're going to talk a little bit about the major components of systems managed storage. First, we're going to talk about the catalog data set or catalog data service. So the catalog data service was adopted from the mainframe implementation, and mainframes did not use file systems. They had a requirement to produce a scalable storage architecture. And it was an object-based architecture as we would define it today, although the terminology did not exist back then. And I'm defining it as an object storage architecture because it had a central database, and the service worked around the concept of having tape cartridges and disk packs that were on a shared channel attached fabric of sorts. And when the catalog data service was requested to provide a data set to a batch process, it would allocate one of those tape cartridges or disk packs for direct channel attachment to the host making the request, allow it to do the read or write I/O, and then release that storage target and return it back to the pool for the next allocation. So you can think of that sort of in the context in the modern IT environment as being perhaps an RDMA attachment over a converged network in a data center. So the requirement to support disk and tape leads to some interesting implications. The disk devices obviously are block architecture devices that support multiple threads and can be shared across multiple processes. However, that is not the case for datasets stored on tape. Tape is a single-threaded storage tier, and there's no way around that. So in order to use the same code path for tape, disk, or anything else, the approach has to be to take a lowest common denominator approach to processing I/O threads. So the abstraction for the catalog data service for the storage service it provides to the batch processing environment is to create a volume set, or if you will, a spanned group of volumes, which have in some sense the same metadata as a file system subdirectory in that they have ownership and permission mask, but they have additional policy attributes that allow for systemic management. So expiration policy would be one of those attributes. Location would be another. It's required to support vaulting between different sites. And lastly, the technology type. So when one creates a volume set, it can be assigned to, say, a disk tier initially, and then as the data ages, deprecated to a lower tier in the storage architecture. So that is that's a transient attribute. So the paradigm for using storage services from the catalog data service would start with accessing a volume set. And that access is by a single process, and it is exclusive access. If I open a volume set, nobody else can open it. Any attempt to do so will result in the second request going into a wait queue. Then we have a set of processes that need to take place after the volume set is accessed. And some of these processes are closely coupled to a technology tier, and some of them will be no-ops for different technology tiers. So for an example, device allocation in a tape perspective has to take into consideration compatibility of media and tape drives. So say, for example, I'm using a specific LTO generation. There would be 3 generations of the drive type that would support read processing on 1 generation of media, and 2 generations of drive type that would support write processing on 1 generation of media. So the device allocation has to take into consideration what the original media type is and what the compatibility levels are with different drives that are available in the overall architecture. So that might not be necessary. That is the device allocation processing on a disk layer. On the other hand, it may be also necessary, just simpler, in the sense that I might have multiple tiers of disk. I might have archive tiers, and I might have performance tiers, and I might have tiers that are somewhere in between those two. Then we have the label processing. In handling particularly removable media, that's a very important capability. You need to be able to, when you're processing a piece of removable media, confirm that you have the right piece of media before you start doing any write I/O to it, of course. And there's also additional functions that have to take place to protect the metadata and to deal with volume spanning. So for an example, when I'm writing to a tape, when I first do the mount, I'm going to read the volume label to make sure it's the correct volume serial number. If it's scratch mount, I start by writing that label. Once I'm doing my write processing, I'm going to wrap every single file with the file metadata, so it's at the beginning and the end of the file. That's standard label processing. We continue to write, wrapping that metadata across every file until we get the early end of media warning. At that point, presumably, I'm going to have just a fragment of the file. It very rarely happens that a full file write happens to align with the end of the physical volume. So generally, I'm dealing with a fragment, so we have to write a intermediate closing label for the file, indicating that it is a fragment. There's another section coming up. Then you have to close out the volume with the closing volume label and start to span into the next volume, which brings about another technical complexity in that generally you don't want to wait for a tape volume to rewind and unload so that you can continue the file write or read on the same drive. So we, as a desirable feature, want to support what's called a hot I/O swap, where we'll allow that rewind unload to take place on one drive while we relink to the job to another tape drive. The read processing, again, is going to be contingent on the label processing to confirm that we always have the right piece of media mounted, that when we do a locate to the correct data set, that it has a label that matches. So these are all belt and suspender approaches to make sure that the integrity of the data isn't compromised. So after the volume set has been accessed and the IOs have been performed, it's necessary to free that volume set so that the next user can gain access to it. So if there's somebody waiting in the queue, the next one who entered the queue with the next highest priority would then get the access to the volume set. This process repeats over and over again. So then using the vault processing and the expiration policy and the reclamation processing and all the other things that go with the catalog data set, eventually the volume set reaches an expired state and it gets scratched, and the storage targets that were allocated to that volume set are returned back to the scratch pool. So this was the storage paradigm that I wanted to bring to the Unix operating environment, but the most significant barrier I had was how to bridge the gap between the abstraction that was presented to the user for a catalog data service versus the way people were used to working with data in the file system space. So the file system has got a lot of limitations. It has a lot of issues with scaling in terms of metadata. It has a lot of issues with not protecting the user from data loss. It has a number of issues that are strikes against it, but it has in its favor the interactive type of user presentation that people have grown accustomed to since the first Unix file system was written in 1970. So it's difficult to take a user who's grown accustomed to dealing with data in a certain way. It has applications that are written to deal with that data in a certain way and turn that entire experience on its head and accept something that's more gruesome to interact with. So I wanted to prevent the user from being exposed to the catalog data service. So the idea I came up with was to create what we call the SMS processes. It's systems managed storage. And those processes are meant to loosely couple the user file system to the catalog data service so as to isolate the latter from the user. So some of these SMS processes would include the automatic archival copy of files that are created and modified within the file system space into the catalog space, where they inherit the versioning provided by the catalog's generation data group architecture. Some of the other processes allow you to, in the file system space, navigate among those versions. If you watched the second video in this series, I introduced the idea of rewinding a file back to a prior generation within a file system, and once rewound, moving forward back to a later version. And that was presented as the paradigm for data protection. Since we never overwrite anything in place in the catalog, we'd only do it in the file system, and we had the capability to restore the file system copy back to a prior generation at will. Another capability that we wanted to provide was capacity management. One of the things that is really cumbersome to deal with is when you're creating or editing a file, not being able to save it because you have an no space error, there's no free space left. So we introduced, well, we didn't introduce, but we took advantage of an HSM process that is referred to as purge restore. The idea of purging a file leaves a file stub with the file metadata, but it releases all of the user data associated with that file. So using the purge process in a free space policy, we can basically choose which are the files that are unnecessarily occupying capacity in a file system to release that capacity, and then have the data automatically restored the next time a user tries to open that file. And we make that process completely transparent to the user, notwithstanding the latencies that may be involved. So for example, if the catalog data service archive target is a Ceph cluster that doesn't have any significant latencies, you will not, for the most part, recognize the fact that the file is being staged back, particularly if it's a small file. On the other hand, if the volume set is currently residing on a tape technology, then you'll have the moment or so that it takes to effectuate the robotic mount of the cartridge, the positioning to the file that you're requesting, and then the restaging of the file data back to the user file system space. Now, lastly, and this really gets to the heart of the approach to scalability, we have what I refer to as a synthesis of virtual file systems. So the concept here is basically that we create a file database for the user file system space that's the aggregation of all the file metadata across the enterprise. The catalog data service, on the other hand, has the copies of the files in a version-controlled service, waiting to restore any one of those files to a file system at any point in time. So when we combine those two things with a database application that allows us to select file candidates based on an SQL query that we would like to have provisioned into a file system, we can execute that query, create the stubs in that user file system, and then present the file system as if it were fully populated and dataful. The user does a listing and he sees all the files with the original file metadata indicating the last access time and last modification time. It has the size of record for the file, but it's actually just a stub. When the user opens the stub in that particular location, a system process goes back to the catalog data service, requests the file that's pointed to by that stub. It's restored locally, and the user now has the full semantics of a file system to access and modify his data set based on whatever catalog data service copy he brought back. So that's the approach to achieving scalability. The catalog data service does not try to be a file system. It just tries to be a highly scalable storage service that can be thoroughly regression tested and services requests in a batch processing manner. And with that said, that's the short synopsis of how the OpenSMS architecture was designed and what the goals were. And with that said, I hope that you'll visit our website and are going to become a participant in our forum and help us to continue to test, develop, and deploy our OpenSMS framework for storage management.